Good afternoon. This will be our second recitation and we are going to solve midterm problems in this case. Now, okay. Here I have a scan of your midterm paper and I might just start solving the problems starting from the second one. Now, the second question is again a Lorentz transformation question. It's quite simple. Now, what are we going to do here is that we are going to have a Klingon flagship with a docking platform of natural length 100 meters long. And then some observer on the Enterprise is going to see this as 80 meters. Now we just write down the formula and then we happen to just over L0 HT over this is 4 over 5 equals to 1 over v square c square, this one. So now we as you all know, square everything and obtain this one. Now if we just happen to solve this, we find that v over c is going to be 5 and we are going to find v to be 0.6 c is the speed of Enterprise. Now that was all for second problem. Moving on to the third problem. This is excuse me. Now we are in this question we are measuring wavelengths of the wavelengths of the hydrogen lines of the spectrum of a quasar observed in our laboratory. Now we have its natural wavelength and then we observe it as some 3 times longer its original wavelength. Now we are hoping to find the shift. We just write down the formula as it was in your books. Now here we stick this given information from the question, then find out 9 equals 1 plus v over c, 1 minus v over c. Then we just do the job. Plus v over c. Now this is 8 here, and now this is 10. Then we find v to be this number, so this 0.8 c is the relative speed. Moving on to the next question. Question 4. We have a metal surface with a work function 5 electron volts. Now we just write the generic formula that here in the front page. I suppose the formula was already given. It's this one. Okay, so now we need to find the lowest wavelength and lowest frequency for the electromagnetic radiation incident on the metal surface that has a work function of 5 electron volts. So just like we just write this, and then we know the relation between the frequency and the wavelength is quite simple. Now that I would not put c here, I would just write it like this in natural units. But this was something I also realized when I had the chance to see your exam paper and like answer key and then have realized and had to remake this video, that we have to use the SI units. So what we're going to do is that now, if we want the lowest frequency for the electromagnetic radiation incident on the surface to emit some photoelectrons, so we need the lowest. So like this part, we might equate it to 0 to find the lowest one, so that we just have to give some wavelength for it to barely emit photons and nothing else. Now that we have this relation, we just write F equals 0, and then we're just going to stick this. And now this was in your front page. This was given, the approximation for this was given. So electron volts nanometers for some wavelength equals 5 electron volts. And now we are going to just calculate lambda as 5 nanometers. Then what we're gonna do is that we know that frequency and wavelength has this relation between them, so we are going to F and find F from here that we do not know. Need to do this. It's quite simple. For the part B of the same question, we need to assume ultraviolet light with a wavelength of 62 nanometers shines on the metal surface. So now we write this same same relation here, and then in the part A we equated this to 0 for us to find the lowest wavelength, lowest frequency for the electromagnetic radiation to emit electrophotons from the metal surface. And now that we are asked to find the stopping potential for this specific one. So we do not know this, but what we know is this. So is electron volts nanometers, 62 nanometers, that shines on it, and then we have 5 electron volts. Quite simple calculation. We find this to be 20 electron volts, and this is 5 electron volts. The answer is 15 electron volts is the stopping function. Now in the part C we have to sketch a plot of the potential versus frequency. Just start by sticking the axis on the grid that was given. Now let's stare at this equation a little bit. Now this is like stopping potential, this is frequency, and this is the work function. So what we realize is this is quite linear, and our graph will definitely be linear. Then what we have to realize is this. Now let's find what are the equations in what are the values that we put on the axis. What are the points that our graph will cross on F and the potential axis. Okay, so let's assume that the potential is 0, so it's -5, as we did in the part A. So here we have this, hence is this. Now this is some F0 that we had actually calculated in part A to be I actually did not. Okay, let me just do it right now. That in part A we found F, C, S, 8 meters per square, and lambda was 12.8. It's like this is nanometers. So give me a second. I have to use calculators for this. Calculators 3. Okay, this is approximately 1.2 or no, 17 was nanometers. Okay, yeah. This meters is the let's see. This is hertz, obviously. So this is F0, that we just put some F0 here to be 1.2 over 17 hertz. Then we go on finding what's going to happen when the F is 0. So now that if you put F to be 0, take F to be 0, now this stopping potential is going to equal minus the work function. This can happen, but like since the frequencies cannot be negative, this part of the line we are definitely not going to use. But since potential can be negative, this minus 5 electron volts is going to be on the y-axis, where our graphs cross at the y-axis. So now then we are going to plot a linear graph, and the other half of the graph is just not going to exist because like negative frequency is something that we do not deal with. So now moving on, moving on to the fifth question. This is really a simple calculation problem. We just have a wavelength given as this one, and then we need to calculate the photon's energy. Now that we just know this to give energy, and we had found out this was given in your front page in the formula sheet, then we just find an energy that one photon has to be 2 electron volts, but the question asks that about 10 visible photons are associated with the photosynthesis reaction. Then obviously we multiply it with 2, and the energy we multiply it with 10, and the energy associated with the reaction is found to be 20 electron volts. That was simple. Then moving on to this first 6 question is that the equation for the dispersion of a massive particle and a photon was given in your in the question. So for each we have to determine the group and the phase velocities. So determining the group and the phase velocities, we are going to use the formula in the PHYS book that was given as. So the equations for the group and the phase velocity are given like this. This is the phase velocity. This is 3.11 of PHYS book, and this is the group velocity. 0.30. So we are going to use these relations. Now we work it out for the photon because it's simple. So the photon's dispersion relation is given as this one. Now the phase velocity over k, ck, k is going to give the c. So obviously the phase velocity of light being c is quite plausible. There's nothing wrong with that. Then we find the group velocity, and obviously now we write it like this. Now that since this was given to be this is not relevant to anything. This since is a constant, not relevant to anything, we just can take it out, and after we took this out, we just find the group velocity of photons to be again c, which is again very plausible. So moving on to a massive particle, we have dispersion relation omega equals mc square over h bar plus h bar k square over 2m. Now the phase velocity is just v over k mc square bar k plus h bar k square 2mk. So writing it again, mc square h bar k plus h bar k over 2m is the phase velocity of a massive particle. Let me put another page. Now that we need to move on to the group velocity of this massive particle, and we just write the mc square h plus dk. Now this equals, since m is a constant, we can take it out, c is a constant, we can take it out, h is a constant. Since this is like all constant, that doesn't bring anything to the equation, it's just like all constants. So moving on to the second term of this equation is that h bar is a constant, we take them out, m is a constant, we take this out, and then we have this one, which is not a constant, so stays, h bar over 2m. Then we just take the derivatives as usual business. hk over m is the group velocity, as we figured. Now we are asked to verify that group velocity is equal to the massive particles velocity. So okay, now for this we need to use the relation for momentum. That was this for a non-relativistic particle, and we know this to equal to be this. Then we just write, now we just stare at this equation and then divide it with m to make this part equal to the group velocity. Now then this just gives us the velocity of the particle is equal to the group velocity. Okay, proven. Moving on. So since there's a typo, we have another sixth question. Now here we have a scattering experiment. In this one, we have a de Broglie wavelength given as some fraction of the Compton wavelength. So we are given the de Broglie wavelength of this. Is given. Okay. Then we use the formula for the Compton wavelength and the de Broglie wavelength. Now, the relation between these two are like this. Wavelength equals this. De Broglie. Compton de Broglie wavelength equals to this. Compton wavelength equals to this one. Now that, and we have this relation, so it's quite simple. Now that just write this h over mc square root 3. Okay, that's perfect. Now we are going to find momentum to be equal to c squared. Then we are going to realize that obviously momentum's original formula for the relativistic particle is this. Then we are going to find out, this is to c. Then we are going to find factor gamma from this equation. Now factor gamma was like 1 over not square root or mu is square root to c. Now if we square everything, or we square c squared 3c squared, this is c squared 3c squared, these are gone. I should square 3 squared 4 squared equals to c squared v 3 over 2 c squared. Then yeah, we just take the square root of whole equation to find this. Now that, so as this thing, we found the speed. Momentum was here already, and we need to find the total energy and the kinetic energy of this. So like we know for the electrons the total energy and the kinetic energy formulas, so just write down the energy is going to be gamma factor of the rest energy. And did we find the gamma factors? No, we did not. So let me first find the gamma factor for the speed. Gamma is 1 over 2 minus 3 over 4. Alright. This is in square root, 1 over 4 in square root, and this is 2. So 2 c squared is the total energy, and then we have the kinetic energy formula, this to be c squared. So we found all the asked quantities. Now what do we have to do is that we assume that the electron that was given in part A is stopped instantly after recoil. So what is the expected minimum wavelength of the emission? So what happens here is that now we have an electron with a relativistic speed, and we just stop it instantly. Then obviously it accelerates to stop at an instant, and this acceleration creates a radiation called Bremsstrahlung, and then we are asked to use the formula again for this. Now we are expected to find the minimum wavelength. So let's just use this example from the X-ray production in your books. That is, and I think in the PHYS book. Now, in chapter 2, you are going to see the formula. It's new. Maximum, it's the minimum. So now what we have to understand is that if the electron is stopped after the recoil, that we are expect to find the minimum wavelength of the emission. For this, we need it needs to be stopped at the maximum speed that it has. Now we just write it down like this. Now that this thing has to be all kinetic energy for it to have minimum wavelength. So it was just you see that now that this electron was moving pretty fast, and now we need to stop it instantly so that all of its kinetic energy turns into radiation, so that we do not omit any of its energy, that we just write it like this. Kinetic energy Hc minimum. So like we need to turn its all kinetic energy to Bremsstrahlung radiation for it to be for it to have the minimum wavelength. Then this one we found as MC square in part A, and we just put it like this, and the minimum wavelength is H over MC. The one can just plug in the necessary values for H, M, and C to find the exact wavelength. So again, we have a Compton scattering question. So now in this case, a photon and a free electron scatters through an angle of 90 degrees. So we need to have an estimate of about the energy of partition after the scattering. Okay. Now that we have to write the relation between its wavelengths and the angle of scattering, which is this. Cosinus. Yeah. And then cosinus phi was given to be 90 degrees. We find cosinus 90 degrees to be 0. So just do not have this anymore. Hence, we just write that the difference between the wavelengths is this one. Now that we have to find some wavelengths according to, now that we know that the energy is the high Hc or lambda. Now we just need to find the electrons wavelength with this relation. So 2 mega electron volts, this is 10 to the power of 6 electron volts equals, and the Hc factor we have learned to be this one, something. So this nanometers is 9. So this is like 10 over 3. It's 9, 10 over 6. So that's, I think, equals 15 minus 3, 12, like 10 or 12 meters. This is the wavelength. So after that we can, let me have another page. After that we found first this wavelength to be 10 to the minus 12 meters, and then we need to find after the scattering, what happens after the scattering. Sorry. After the scattering, this is what is going to happen to the wavelength, which we find to be this. Now let's go back to your front page and then take all of this values from the front page to find the eventual number, and then we are going to add this, the wavelength that we found, and then we are going to find the wavelength after scattering. So this in your answer sheet is given. This one, I suppose I made, this is picometers. The picometers was, I suppose, picometers. Okay, yeah, picometers. This thing. That's 12 meters. Look, I believe you can just calculate this really easily. I've made a mistake calculating this, so I actually do not want to go on to doing that again, because every mistake makes me just record these videos again, which I do not want. Of course, this was 1 picometer, again 1 picometer, and then after the scattering, the wavelength expected is this number. Now, since we have a different wavelength after the scattering, we have a change in the energy after the scattering. Again, we use the formula, this, but now the energy and the wavelength are all primed. Electron volt nanometers. Just stick this number in and just find this. So this is the energy of the electron after the scattering. Now that we have done this, Okay, so we have question question 8. It's an experimenter aiming to measure simultaneously the wavelength and the position of a photon. Determines the wavelength as this nanometers with a precision of 1 per million. What is the minimum uncertainty in the position of the photon? Okay, these questions like our favorite questions because we just have to work the uncertainty principle, and it's quite simple. Now for the part A, wavelength and the position of the photon, we are going to use this relation. So, and the position, because we have the position and we have to have the momentum. Now, one per million being number 6. Now we find the wavelength of the photon as such, but we have an error bar in the degree of 1 in a million. So if we write it like this, this is the difference between the actual and what might be. So this is going to give us some estimate of the precision. Then we obviously have the uncertainty principle right here, that we are going to find this factor, because we know we are actually asked to find the uncertainty in the position. What we need to know is the uncertainty in the momentum, so that we can just relate it to the position. But we know that the wavelength and the momentum are related. The wavelength and the momentum are related like this, right? So if we happen to find this, how do we write it? We are going to have it like lambda is going to give us lambda or lambda. Then this is that's why it cannot happen, because like these are like constants. So now that we just have P as the lambda or lambda, if it makes sense to you. So now since we have this, we need to find EP equals P or lambda. Now that we do not know the momentum, but we can just again stick this here. So yes, and we know this to be this is a constant, this wavelength. Do we actually need to know it? Know this wavelength? I suppose I'm sorry, this factor. This. Is 10 to the minus 6, 1 in a million, and this is momentum. So we can just roll with that. So now we use this relation del x del p equals del x 1 in a million this bigger or equal to 4 pi. Okay, now since we have this, the uncertainty in the position has to be bigger than this factor over here. This is like this, pi 16. So well, if we have to take p as 3, okay. Okay, wavelength was given. We just write the wavelength like this, we solve this, and answer key that was given as 2. Okay, let me check it again. It's 9, 14. Okay, so when it does not really matter, just calculate this and you probably are good to go. Let's explain. So in part B, we have to find the uncertainty in the frequency of the photon. So uncertainty in the frequency of the photon. Now for a photon, we know that this holds, right? Okay, now we know it uncertainty in the wavelength is 1 in a million, and then we have to this point. Now since c is a constant, it just does not really matter, so we just can write it like this. So the uncertainty, so that the ones that the uncertainty that the allowance of us to make some mistake in measuring the wavelength is actually the same order of magnitude as we are allowed in the frequency. So then we just write it like this. We are asked to find this. We know that the wavelength was actually given 8 nanometers. Asked to find this one. The frequency just that's just nanometers, 3.8 meters per second, and some frequency. So that frequency is 3 seconds and 40 plus 9 meters. And this is something hertz, obviously. So that take this number, put here, then we know this to be equal to 10 to the minus 6. So solving it all together, 8 per second, 80 9 meters. over 10 meters. Is going to be uncertainty in the frequency. If we calculate this, we are going to find something like 16. So, as one might see, the uncertainty in the frequency will be quite large. Okay. Okay, I think we had another question, but I forgot to scan it. Let me just scan it and come back real quick.